Dear children, in the last session we have seen the Euclid's division lemma. Using this Euclid's division lemma, we are going to deal with the problems which are given in the examples and in exercise, that is exercise 2.1. Okay. See, you know what is the lemma. So, the lemma says that if a and b are integers, then we can say a is equal to b cube plus r for unique q and r. That is, a is equal to b cube plus r is a restatement of long division method, where r lies between 0 and b, but r should be less than b, that is the numerical value of b. You know these already. That is, I am going to repeat, a is equal to b cube plus r, where 0 less than or equal to r less than the numerical value of b. We have seen this in the last session. See, based on this we are going to deal these sums. See the first example, it says that there are 34 cakes. 5 cakes should be packed in a box. How many boxes can be packed and how many cakes will be left without packing? Okay. So, in this 34 acts as a dividend. So, A is 34 and B, the divisor is 5, that is we are going to divide the cakes into 5s. So, B is 5. So, we are going to write in the lemma statement, that is we are going to divide 34 by 5. So, if you divide 34 by 5, we will say that 5 into 6 is 30 and 4 will be the remainder. So, 5 into 6 plus 4. So, this is in the form A is equal to B Q plus R, where Q is the quotient which is 6. So, there should be 6 boxes. So, 6 boxes will be there and 4 cakes will be, yes, very good, left over. 4 cakes are left without packing. So, let us go to the next sum, where Q and R are asked. You are going to find the quotient and the remainders in the given A and B's. So, first in the first one, A is minus 12 and B is 5. So, here we are going to write in the statement, that is A is equal to B Q plus R in the form, and we are going to find Q and R. We have to keep in mind that since R is non-negative, BQ is always less than or equal to A. So, keep that in mind and do this sum. So, we are going to split A minus 12 is equal to BQ. So, 5 into Q plus R. So, we have to fill what Q is and what R is. So, see, invariably we will say that 5 2s are 10, 5 2s are 10. So, 5 into minus 2 is minus 10 plus R, R is minus 2, but here R should not be negative, R is non-negative. So, and one more thing, this BQ should be less than A. So, more negative should be there for BQ. So, what is more negative than minus 12? So, which is more negative? Minus 15. So, we have to say that 5 into minus 3 plus, as this becomes minus 15, we are going to add 3 with that to get minus 12. So, for a negative number, we have to get the more negative value as BQ, because more negative means it is, the value is less than A. Always BQ should be less than or equal to A, keep that in mind. So, minus 12 can be split as 5 into minus 3 plus 3. So, in the place of Q we have minus 3 and in the place of R we have 3. So, these are the answers. Here Q is minus 3 and R is 3. In the next sum, A is equal to 17 and B is minus 3. So, 17 is equal to B is minus 3 into Q plus R. We have to find the values of Q and R. We should get 17 here, a positive number. So, Q should be negative to make it positive. So, what is the number which is less than 17, which is divisible by 3? The least number which is divisible by 3 and less than 17 is 15. So, to make it 15, we have to take q as minus 5. So, minus 3 into minus 5 becomes 15. We need 2 more. So, plus 2. So, which means q is minus 5 and r is 2. Very good. Here we are going to apply the long division method in this also. So, minus 19 is equal to minus 4q plus r. We need to search for q and r now. So, keep that in mind, this product should be less than or equal to this number. So, we need to get more negative. So, the number which is divisible by 4 and more negative than minus 19 is very good, minus 20. So, I have to make this as minus 20. So, what should be substituted in the place of q to get this minus 20? Very good, 5. So, minus 4 into 5 becomes minus 20 and we need minus 19. So, we need to add 1 with that. So, plus 1, which means q is equal to 5 and r is equal to 1. Can you understand these sums? Let us move on to the next sum. Okay, see this sum. In this example, show that the square of an odd integer is of the form 4k plus 1 for k is an integer. Okay. What do you mean by odd integer? Odd integer can be represented as 2k plus 1. Very good. So, as k is here, I am going to represent it as 2q plus 1. Okay. Any odd number is of the form 2q plus 1, where q is an integer. So, this is an odd number, that is odd integer. See, if we square this odd integer, the square of an odd integer, so if you square this, so 2q plus 1 the whole square, what is the form of this? So, we are going to expand using a plus b the whole square. So, a plus b the whole square means a square, that is 2q the whole square. So, 4q square plus b square is 1 square, which is 1 plus 2ab. So, 2 into 2q into 1. So, 4q. So, I can rearrange this as 4 into q square plus q plus 1. Taking 4 fact out, we can say that 4 into q square plus q is plus 1. So, and 4 into q square plus q can be replaced with k plus 1, for k is an integer. So, we can arrive at a form as 4k plus 1. So, what is written in the form 4k plus 1? Square of an odd integer. So, we have proved. See, let us go to the next example. If the HCF, highest common factor of 210 and 55 is expressible in the form 55x minus 325, find x. First, let us find the HCF of these two numbers. The numbers 210 and 55. So, using Euclid's division algorithm, we are using the algorithm of Euclid and finding the HCF. So, it can be written as 210 is equal to 55 into some number plus r. So, how many times we are going to divide 210 by 55? We know that it is 3 times. So, 3 into 55 is 165. So, yes, 45 remains. So, 45 is the remainder, and then we have to see whether the remainder is 0. No, it is not 0. So, we have to take the divisor and the remainder and apply the algorithm. So, 55 is equal to 45 into some number plus a remainder. So, 45, how many 45s are there in 55? Only 1, yes, plus 10 is the remainder. Here remainder is not 0, we have to proceed. So, the divisor is 45 and 10 is the remainder. With these two numbers, we have to use the algorithm. So, 45 is equal to 10 into some quotient plus some remainder. So, you are going to divide using long division method. How many tens are there in 45? Yes, 4 tens. 4 tens are 40, the remainder is 5. Since the remainder is not 0, we have to proceed further using 10 and 5. So, 10 can be written as, very good, 5 into 2 plus 0. Yes, very good. So, we have got the remainder 0. So, the divisor where we get the remainder 0 is the HCF. So, HCF of these two numbers is 5. With this HCF, we have to proceed further. So, we are going to express this 5 as 55x minus 325 is equal to the HCF, which is 5. Can you understand the statement? If the HCF is expressible as 55x minus 325. So, we have written the statement and take this minus 325 that side and it becomes, yes, plus. So, plus 325 plus 5 becomes 330. So, 55x is equal to 330, which means x is equal to 330 divided by 55, which is 6 times. Very good. So, x is equal to 6 is our answer. Shall we move on to the next sum? See, in the sum, the greatest, you are going to find the greatest number which divides 445 and 572, leaving remainders 4 and 5 respectively. That is, on dividing by our number, these numbers leave remainders. So, first let us subtract these remainders and get the dividends. So, from 445 we have to subtract 4 to get our first number. So, the first number is, yes, 445 minus 4. So, 441 is our first number and the second number is, it is 5 less than this 572. So, 572 minus 5. So, 567 is our second number. So, using these two we are going to get the HCF. So, which is the larger number? Yes, 567 is our larger number. So, that should be written as A. So, we are going to find HCF of A and B using division algorithm. So, 567 is equal to 441 into some quotient plus remainder. How many 441 will be there in 567? Yes, only 1 once. Then what is the remainder? So, subtracting we get, yes, 6 and here 2 and here 1. So, 126 is the remainder. Remainder is not 0. So, we have to proceed using the algorithm. So, 441 is equal to 126 into some quotient plus remainder. How do you find this quotient? Using long division. So, we can use the long division method. So, 441 should be divided by 126. So, that means it is 3 times. So, 3 6 are 18, 3 2s are 6 plus 1, 3 1s are 3. So, subtracting we get, so 13 minus 7 is 6. So, remainder is 63. So, quotient is 3. So, 126 into 3 plus the remainder 63. So, we are going to restate the long division method as you already know. So, remainder is not 0. We have to proceed again using these two numbers, that is the divisor and the remainder. So, 126 is equal to 63 into some quotient. So, you know that is 2 times 63 is 126. So, quotient is 2, but the remainder is, very good, 0. So, as the remainder becomes 0, we can state that this is our HCF, that is HCF of those two numbers is 63. Okay. So, using the same algorithm we have to find the HCF of 3 numbers in the coming sum. So, how to find the HCF of 3 numbers? So, first we are going to apply the algorithm for the first 2 numbers. You can take any 2 numbers and get the HCF of those 2 numbers. Using this HCF and the third number, we have to proceed with the algorithm and find the HCF again. That is, first get the HCF of 2 numbers, with the HCF and with the third number we have to find again the HCF. So, we are going to do in this sum. So, these 3 numbers are to be found HCF. So, we can take any 2 numbers for this purpose. First, let us take these 2. Among these 2, which is the larger one? Yes, 504. So, 504 is equal to 396 into some number, that is our quotient, plus remainder. How many times will it be? Yes, only once. So, subtract 14 minus 6 is 8, here 9 minus 9 is 0, and here 4 minus 3 is 1. So, 108 is our remainder. So, we have to proceed with 396 and 108. So, we have to find the quotient and the remainder. So, you can use long division method. So, you will get 3 times. So, 3 times 108 is 324. So, subtract 324 here from 396. So, our answer is yes, 72. So, 72 is our remainder, where we have to proceed again with 108 and 72. So, 72 plus some number plus the remainder. How many times will it be? Yes, only 172 will be there in 108. So, the remainder is very good, 36. So, with 36 and 72 we have to proceed like 72 is equal to 36 into some quotient plus remainder. So, what is our quotient? Very good, it is 2 times. So, plus, very good. As the remainder is 0, we have to say that 36 is our HCF. So, 36 is the HCF of these 2 numbers only. Okay. So, we have to proceed with the third number and 36. So, find HCF with or HCF of 36 and 636. So, 636 is obviously larger number. 636 is equal to 36 into some number plus remainder. So, we are going to divide by 36, divide 636 by 36. So, our answer will be ones. So, 13 minus 6 is 7, here 2 and 276. See, in these larger numbers we can follow a smaller method, that is in 27 we are going to leave the last digit 6 and here also we are going to leave this digit. So, 27 and 3, how many 3's are there in 27? Think it of, you will be getting 9, but as one more number is there, we have to come to the previous number. So, we can check with 8 and further we can check with 7. If we cannot find the answer in 8, we have to check with 7. So, it is 7 times. So, 7 6 are, yes, 42, 7 3s are 21 plus 4, 25. So, we are subtracting. So, our answer is 24. So, 24 is a remainder and 17 is a quotient here. So, we have to place 17 here and 24 here. Since the remainder is not 0, we have to proceed as 36 is equal to 24 into some quotient plus some remainder. So, you know that yes, it is ones. 124 is 24 and the remainder is 12. So, further we are going to proceed with 24 and 12. So, 24 is equal to 12 into, very good, 2 plus 0. So, we stop here as we got remainder 0. So, the HCF is 12. So, HCF of all these 3 numbers is got to be 12. Have you understood, ma? Okay. See this sum in exercise 2.1, fifth sum. Prove that the square of any integer leaves remainder either 0 or 1 when divided by 4. See, any integer is of the form 2k plus 1 or 2k, that is odd number or even number. So, we can write the integer as 2k or 2k plus 1. So, these are the forms of any integer. This is even number and this is an odd number. So, we have to prove that the square of this integer. So, we are going to square this integer. So, we are going to square this form, that is if the integer is odd. If the integer is odd, we will be having it in the form as 2k plus 1. So, squaring we are getting in the form a plus b the whole square. So, expanding we know that 4k square plus 1 plus 4k a square plus b square plus 2ab, and taking 4 out in these two terms, 4 into k square plus k and here plus 1. So, if we replace this as q, we will be getting 4q plus 1. Okay. So, here that means while dividing this by 4, we get the remainder 1. Can you understand? So, this is of the form a is equal to bq plus r. So, a is our square and b is the number 4 and q is our quotient. Here r is 1. So, for any odd number the remainder is 1. If you square we get the remainder 1. Let us take the even number. If the integer is even, we represent it as, very good, 2k. So, 2k square of the integer becomes 2k the whole square, which is 4k square. If you take k square as q or some q1, 4q1, there is no remainder, that is remainder is 0. So, here the remainder is 0 and here the remainder is 1. So, these are the only possible ways if you divide the square of an integer by 4. So, we have proved. Let us move on to the next sum. See, if D is the HCF of 32 and 60, find x and y satisfying the equation D is equal to 32x plus 60y. First, let us find the HCF of 32 and 60. Okay. So, what is the HCF of 32 and 60? Using division algorithm, we can write the larger number as A and the smaller number as B. So, 32 into some quotient plus R. So, you know that only once, remainder is 28. So, we are going to follow 32 is equal to 28 into some quotient plus R. How many times? Yes, only once, plus the remainder is 4. Again we proceed, 28 is equal to 4 into, yes, 4 into 7, very good, plus remainder is 0. So, as we get the remainder 0, we stop here and say that the HCF is 4. Here we have one more job to find x and y. So, this number is taken as D, that is D is 4 here. So, 60 is equal to 32 into 1 plus 28. So, we need to relate with 4. So, I am going to replace this 28 as 32 minus 4 because I have to get 4 in our statement. So, this 32 let it be plus 28. Here 28 is there with 32 and 4. So, we are going to take this 28 as 32 minus 4. So, 32 minus 4, which means 32 into 32, 32 plus 32 becomes 2 times 32. So, 32 into 2 minus 4 is 60. We need, yes, 4 here. So, minus 4 taken as plus 4 here, and this is 32 into 2 minus 60, 60 into 1, or we can say that plus 60 into minus 1. See, compare this statement with the given statement. D is equal to, D is our 4, 32 into x. So, x is 2 and our y is minus 1. Okay. See, in this exercise 2.1 ninth sum, a number is divided by 88, leaves remainder 61. That is, it can be written as A is equal to 88q plus 61. And the same number when divided by 11 leaves remainder r. We are going to find that remainder. So, we have written A is equal to 11 into q1, some other quotient, plus the remainder r. So, these two numbers are one and the same. So, equating these two, we get 88q plus 61 is equal to 11q1 plus r. So, we can have 88 as 11 into 8q. That is, 88 can be split into 11 into 8, this q, and 61 can be split as 55 plus 6, as this is divisible by 11. So, we can take out 11 as a factor, and this is 8q plus 5 11s are 55, so plus 5, and we have one more plus 6. So, if you equate these two, we can observe that q1 is replaced with 8q plus 5 and r is replaced with 6. So, the remainder here is 6, and let us move on to the next sum. The sum says that two numbers, consecutive integers, are co-prime. We have to prove that. So, we can take any two numbers as x and the next number will be 1 more than x. So, x plus 1. So, we have to find the HCF of x and x plus 1. If the HCF of any two numbers is 1, you know it very well that those two numbers are co-prime. So, first find the HCF of x plus 1 and x using Euclid's division algorithm. So, x plus 1 is equal to x into 1 plus remainder 1, and then as the remainder is not 0, proceed with x and 1. So, x is equal to 1 into x plus 0. Here the remainder is 0. On dividing by 1, x gives remainder 0. So, the divisor is our HCF. Here the divisor is 1. So, HCF is 1. We come to know that x and x plus 1 are co-prime. That is, consecutive integers are co-prime numbers. And there are some more sums which we have dealt in the same pattern already. In the last session, we have done some similar sums as sixth sum. So, go proceed with all those subdivisions given in sixth sum, and also try the seventh sum which I have done already in the same pattern. Okay, so far we have seen some problems using Euclid's division lemma. In the next session, we are going to deal with some new topic. Thank you.